So welcome to the fifth lecture of module 6. So today we will concentrate on a special type of or a special class of transducers, that is strain gauges. So in the last video I have discussed about LVDT, its operation principle, construction advantages and disadvantages. So today we'll see what is a strain gauge and how that quantifies the strain or the stress or the force applied. So let's first see why these strain gauges are required. See, machines and structures are designed to carry some load, so they have to withstand that load without much of deformation or failure or breakdown. So how to check for that design load? So one index for determining the stress is one index is actually the stress. That is, what is stress? That is the force per unit area. So per unit area, how much load it can withstand, how much force it can withstand. So that is what is stress. So we have to find what is stress. So stress itself cannot be directly found. We cannot find stress directly. We can actually find the deformations, the elongation or compression, and that is actually known as strain. So strain is actually a deformation, that is elongation or compression caused by stress. So stress can be indirectly evaluated from strain. So that is how these transducers got the name as strain gauges. For example, we usually find longitudinal strain, that is nothing but delta L by L. So this is my original length. What is the change in length? So that will be in micro strains. So we have seen what is Young's modulus. So Young's modulus is nothing but axial strain or longitudinal stress by longitudinal strain. So sigma A by eta A, unit is kilogram per centimeter square, because strain doesn't have any unit. So whatever unit is of stress, that is kilogram per centimeter square. So this is very important. Now we usually plot it. When we plot stress versus strain, we usually expect a linear curve, but the linearity is only up to a point. So this is the point of linearity where you can check the slope, take the slope. After that point, the elasticity starts. That is the inelasticity starts. That is this is the point of elastic limit. Also after that limit, the linearity decreases and the non-linearity creeps in. So the linearity ensures, or linearity exists only at the point, till the point where elasticity exists, that is till the elastic limit. Beyond that, non-linearity will creep up. So beyond, there is a point beyond which the material ultimately breaks due to breaking stress. So we have to concentrate on the linear region. Now we'll see some mathematical things. That is, before going into the details of strain gauges, we were talking about the longitudinal strain. Let me take a material of dimensions x, y and z. So if I apply a load in this direction, or if I apply a force in this direction, that is from in the x-axis from left to right, you can see that initially this was my x, it got extended by delta x. Initially this was y, it reduced by delta y. Initially this was my z, it reduced by delta z. So one important point that we have to see is when we do apply a force in one direction, the opposite or the other two perpendicular directions, there are lateral compressions or the lateral reduction. Okay, that is, in the lateral directions, compressions takes place or reduction takes place while we apply the force in the other direction. That is, when we apply the force in x direction, we have reduction along y as well as z. Now let me go into the equation. That is, this is my longitudinal strain, which is given by eta x, that is sigma x by Young's modulus E. This minus sign is due to the contraction in the y direction, as well as this minus sign is due to the contraction in the z direction, which I can write with in relation to the Poisson's ratio. What is Poisson's ratio? Poisson's ratio is nothing but the ratio of lateral strain to longitudinal strain. So for most of material is positive and it's taken as 0.3. So minus Poisson's ratio sigma x by E. So you can convert this in terms of my longitudinal strain, but there is a minus sign, multiplied by the Poisson's ratio. Similarly, the lateral strain in z axis is minus Poisson's ratio nu sigma x by E. So combining everything, you will get it as this one, that is sigma x by E, all those things. Okay, so this is very important, that is the effect of Poisson's. Why the Poisson's ratio is here? Because when we apply the force in x direction, there is contraction or compression along the other two perpendicular direction, that is y and z. So that is one point I have to stress. Then we'll move on to the different types of strain gauges. That is, there are two types of strain gauges, that is bonded strain gauge and unbonded strain gauge. There are many other types of strain gauges like mechanical strain gauges, optical strain gauges, electrical strain gauges. We will be concentrating only on the electrical strain gauges. So what is the importance of electrical strain gauges? The strain or the deformation or the stress is quantified into electrical quantity. That is how we establish the electrical transducers. So we have electrical transducers or electrical strain gauges where the resistance of the change in resistance of the material is taken care of. That is, we know that R is equal to rho L by A. So when we apply some strain or force, what happens? Length increases, area decreases. So what happens when length increases and area decreases? Obviously the resistance varies, and this change in resistance can be converted into a change in voltage, and that change in voltage is will correspond to some strain or stress. So there are mainly two types of electrical transducers, that is bonded strain gauge and unbonded strain gauge. So what is the importance of bonded strain gauge? So bonded strain gauge is that we have a wire which is usually made of platinum tungsten alloy, and that is bent in this shape for a flat grid type, so that this is the axis on which we apply the force. So this direction will take care of the longitudinal strain, and we have, so this wire is actually bended and it is actually formed in the form of a grid like this. So this is meant to take the longitudinal strain, but these small bends here will take cross sensitivity, that is lateral strain also, which is normally not needed. That is why we always, or designers always, try to keep the lateral strain or the cross sensitivity less than 2% of the longitudinal sensitivity. So we have to keep this as small as possible, or the bends as small as possible, and make this as long as possible. Now this is glued using some insulating adhesive to some backing. So this is some backing or support which will take the strain from the specimen. So this backing will absorb the strain from the specimen. So this wire grid is actually glued or adhesed to this backing, where the backing will take the strain from the specimen. Okay, so this is the side view where you can see that we have the wire here, we have the cement or the bonding cement or the adhesive, which is a non-insulating one, and this is actually glued onto a backing. So this backing will take the strain from the specimen. Likewise, next is a wraparound. Okay, so this is actually simply again a mesh which is actually glued onto a paper tube or a thin cardboard piece. Okay, so this is actually glued or attached to a backing which will pick up the strain from the specimen. You can see from the side diagram that is there are two layers of wire which are cemented to the backing, and the backing will absorb the strain from the specimen. And we have the leads here, and here one advantage is that this will not take the cross sensitivity because we don't have bends or something like that. And then we have, you can see two layers of wires, so these two layers will have different transfer characteristics. And so different transfer characteristics in the same, they will be giving output in a different way for the strain. So two different transfer characteristics is highly disadvantageous. So we normally will not prefer a wraparound type, although cross sensitivity is not here. Now we have another important type, that is single wire type, where there are so many single wires, they are attached at the ends with some strips. So there are some strips, these wires are attached to that strips. So you can see that there is no continuity, although electrical continuity is here, but the material has discontinuity here because this wire is of some material and this strip is of some other material. Now this arrangement is again glued onto a backing. This backing will absorb the strain. Okay, so this again takes care of cross sensitivity. With this has minimum cross sensitivity. And then we have another type, that is a Bhuvan type, where we have the same grid wire with all the bends, but they are actually enveloped inside a textile, and they are attached to a silk cloth, a textile wrap. This one is actually, so the backing is actually a silk textile where we are attaching the wire. So this whole setup can be wrapped around a leather belt or a leather some leather straps or something like that, so that you can know the strain on a leather belt or a strap. Okay, so this one is mainly for measuring large strains, especially in leather materials. Okay, so this is all about the different types of bonded strain gauges. So altogether you can see that bonded strain gauges means the wire is actually attached to some backing, and the backing absorbs the strain from the specimen. Okay, so why they are called bonded? They are called bonded because they are attached to a backing. Now you can see another class of material, that is called unbonded type, where you cannot see any backing. That is, see there are some pictorial representations here. That is, see the first one, we have about 6 insulation posts, and on the insulation post you have the fine wires, the strain wires, which are made of platinum tungsten alloy, and you have a cross arm here which takes care of the force on the specimen. So this is my specimen, so I'm applying the force on this cross arm, which is my specimen. So this strain on the specimen will be given to the wires, strain wires. So they will pick up the strain wires directly from the specimen without any backing material. That is why they are called unbonded. They have no bonding to any backing material. They directly takes the force from the specimen to the wires. So here also you can see that this is another type, that is there are 4 wires. So one end of each wire is attached to the fixed base, and the other 2 are attached to the moving body. Okay, so this has an advantage that if we move this movable arm from left to right, we can see that 2 wires will elongate and the other 2 will contract. And if we move from right to left, another pair of wires will contract and another pair will elongate. So this is what is called the unbonded type, because they are called unbonded because the wires are directly connected to the specimen. There is no intermediary backing material between the wires and the specimen. Okay, so these are the main classification, and there is one more classification, that is the foil strain gauges. Another class of, that is, instead of wires we have foils, which has more advantages than the wire strain gauges. We'll discuss that in the next video.